I was asked to talk about mission options that are consistent with the GER, Global Exploration Roadmap, which is put together by an international set of space agencies, including NASA, which is one of the signatories. Jack Burns is one of the former LSI PIs, and Hopkins and Pratt are two members of the Orion team at Lockheed Martin. What we've been looking at is how to utilize specifically Orion to accomplish some of the GER goals. To introduce the GER, I know we'll cover a lot of this tomorrow, but for those of you who won't be here, the GER outlines a plan that extends human exploration beyond low Earth orbit. It includes multiple destinations, the Moon, asteroids, and eventually Mars. And it highlights the need for a robotic program that serves as a precursor explorer or explorers, then as a parallel mission element partner before we have a fully developed human exploration program. This is a chart that comes right out of the GER, and it shows some of the elements of the lunar robotic program that were at least envisioned when this appeared. And I should stipulate that this is going to be revised, and I believe Kathy Lorini will tell you that next year a new edition will probably be appearing. The timeline starts here with Laddie, and it runs through a series of missions dominated by the Roscosmos, the Luna series, Luna 25, 26, 27, 28, and 29. Resolve was in this part of the sequence. Tony told you about this earlier this morning. Not part of the GER report was the Chinese plans, so I've annotated the diagram from the GR with a few other mission elements. One of the aspects of the GR that I think is very important to understand is that it articulates the need for developing a lunar surface capability and the importance of sample return. This is another chart out of the GER. A lot of people don't appreciate that it has quite a large number of lunar missions within its scope. And for those of you who want a take-home card of this diagram, you'll find that in the other room on a table with a lot of handouts. I'm going to focus on this part of the diagram. There's eventually going to be, estimated in 2023-24, according to the GER, the capability of human-assisted sample return. Downstream, we hope to have humans to the surface. In terms of developing the human exploration elements, there's two components thus far. There's NASA's SLS and Orion vehicles, and that is being paired with ESA's service module. Okay, so this is how one of the architectures or the scenarios that we're envisioning for using Orion with the ESA service module, flying it to either the Earth-Moon L2 location, putting it in a halo orbit there, or flying it in a distant retrograde orbit also in cislunar space. Both of those will get you within 60 to 70,000 kilometers of the lunar far side. And so you see the vehicle in this pictorial above the lunar far side, maintaining communication with the Earth, as well as maintaining communication with a surface asset, in this case a rover on the lunar far side. This type of mission would demonstrate Orion in deep space and with a high-speed Earth reentry. It would generate a 30 to 35-day mission into translunar space. Crew would travel 15% farther than Apollo and spend 3 times longer in deep space, and it would give them an opportunity to practice teleoperations, which is a Mars-forward capability, as you see illustrated here. From the science perspective, it would allow us to land and explore a region within South Pole-Aitken Basin, for example, within the Schrödinger Basin. Geologic measurements can be made in situ. A sample can be collected and returned to Earth. And in addition, at the end of the mission, after the geology has been done, an astrophysical system could be deployed and remain active over an extended period of time. And this is the type of mission concept that we're continuing to explore at greater levels of fidelity with the Orion team at Lockheed Martin. Okay, So you might ask, where on the lunar surface would you explore? And I've already given you some hints of that, the SPA Basin and potentially Schrödinger Basin. You know, you can articulate sites based on your favorite locations. Well, I want to emphasize that we actually looked at this in a very objective way. We started with the scientific objectives articulated by an NRC report called the Scientific Context for Exploration of the Moon, which had a number of major hypotheses and themes and 35 investigations for future spacecraft missions. Some of the big ideas to be explored is the giant impact hypothesis for the origin of the moon, lunar magma ocean hypothesis and fundamental principles of planetary differentiation, and the lunar cataclysm and inner solar system cataclysm hypotheses. Okay. We conducted a series of studies over 6 years of asking the question where on the lunar surface you could conduct those. That produced a global lunar landing site report, and those results have been briefed to HUMD at NASA headquarters, SMD at NASA headquarters, NASA's Human Spaceflight Architecture team, among many other organizations. Some highlights out of that report is Schrödinger Basin on the lunar far side within the South Pole-Aitken Basin is the location where the largest range of objectives can be addressed. For studies of polar volatiles, Amundsen crater may be a better target than Shackleton, and most of the NRC objectives can be addressed within the South Pole-Aitken Basin if that is the sole location that you can go to. As I said a moment ago, Schrödinger seems to be a high-value scientific target. There it is within South Pole-Aitken Basin. This is a list of all of the investigations within the NRC report that can be addressed by missions to Schrödinger Basin. And there are some others. In general, a majority, or larger than 50% of the objectives in that report can be addressed within Schrödinger Basin, if that's the only place you can go. For those reasons, we've conducted a large number of detailed studies of Schrödinger Basin. This actually began when we were looking at this as a human landing site. Our own group and Mark Robinson's group at ASU took stabs at this. Looked at several landing sites where crew could explore Schrödinger using the Lunar Electric Rover. We don't have a human-rated lunar lander, so we can't actually conduct this type of mission. This is the landing site, one of the landing sites in those human exploration activities, and some of the stations where crew could collect samples. Because we don't have a human-rated lunar lander on the books right now, we've been revisiting Schrödinger and asking the question, how might one explore it with a robotic asset in the context of the GER's human-assisted sample return mission? And one of the more interesting sites is this region between a pyroclastic vent with ISRU potential and this peak ring with some important geologic interests. Let me go back here. So this is, whoa. I see something on the iPad, but you're not seeing anything on the screens. Yes? Okay. Can I get some help, Ricky?
Stand by, we're working on this.
Thank you. So let me talk you through this because I know we're short on time. I show you a geologic map and an LROC image, or a high-resolution image of this landing site with a series of stations. Thank you very much, Ricky. This is a geologic map showing, this is the pyroclastic vent here. Here is pyroclastic deposits, a couple of other geologic units. We envision landing here and then doing a series of stations along the uplifted peak ring and returning to the pyroclastic material, collecting the sample, putting it on board in an ascent vehicle, which would then be launched towards Orion in the DRO or L2 position. This is a map just to simply show you we've done our homework. This is a slope map, so we've made sure that our rover isn't going anywhere that it wouldn't be able to access. We've also done a lot of detailed studies using the M-Cube data so we can identify the lithologies that would be sampled. In fact, this has been carried to such a high level of fidelity, we've actually identified specific rocks that we can collect. And so actually, if I can echo a point that Mark made, there is absolutely no reason why we cannot go tomorrow with this type of mission. We do not need additional precursor missions to get to the lunar surface. We have everything we need to know. Okay, we've also done illumination studies, which you can see running here in this GIF movie to identify the best time for the mission. Interestingly enough, there are certain months of the year where you have better illumination, and there are certain years that are better than others. This interval, 6 August 2021 to 19 August 2021, happens to be the best out of a 5-year period that we conducted the study in. Ricky, we're going to skip this video. This is simply a video showing irradiance, and I'm skipping that because we had that little hiccup with the slide. Okay. People have oftentimes articulated that Schrödinger is also a good site to collect an SPA impact sample. I'm not doing anything, Ricky.
Any question?
Okay, so I'll see if I can manually drive this backwards. Schrödinger occurred within the South Pole-Aitken Basin, and so the question is there South Pole-Aitken Basin material within Schrödinger? And this is a map of the iron anomaly that characterizes SPA impact melt material within the basin. This is the part of Schrödinger that carries that anomaly. And so the idea is that if you collect samples within this region, you will contain or pick up samples that include SPA material. In particular, the basin walls of Schrödinger actually probably cut through that SPA impact melted material. These outcrops here have been identified using M-cube data as having mineralogy that is consistent with the SPA impact melt material. And so, in fact, here's an example of one of those outcrops. This is a NAC projected view. So the rover could be down here and drive up to these outcrops and collect the samples. And again, we've done the slope analysis to make sure that that is absolutely feasible. So we argue that you can actually collect samples to identify the age of Schrödinger and potentially the age of the South Pole-Aitken Basin, therefore bracketing virtually the entire basin-forming epoch on the Moon. Okay. Thank you very much. So I have then just 2 final slides. With the Orion time, we've been, we've been evaluating the communications that we would have from Orion vehicle in both an L2 and a DRO orbit. I'm just going to show you the L2 results today. If you come to the GER meeting tomorrow, I will do the trade study between DRO and L2. From the L2 halo position, everything within this circle has continuous, that is 100% calm with Orion. Here's the SPA basin for orientation, and here's Schrödinger. This is a chart showing how much our calm coverage is. Within a 27-day lunar period, all the areas with green, we have 16 days of continuous calm. That is, we have the daylight period completely covered with communications. Okay, we've done also an orbit analysis, and here's actually how that mission would unfold. We would initially launch the robotic asset. It would be in a stationary orbit waiting for the crew to launch. Once crew had successfully launched, the lander and rover would go to the lunar surface. Then Orion would come out. It would loop around the Moon. It would go into the halo orbit. All of these areas where the lines are green are areas where they have continuous or calm with the lunar surface, the rover asset, the sample collecting asset. The sample, once it's collected, then is launched in an ascent vehicle, which rendezvous with the Orion vehicle, and then the Orion vehicle returns to Earth with that sample. So in conclusion, we found that the Schrödinger Basin is one of the highest landing site priorities based on the NRC 2007 objectives. It can be used to test 2 of the major science hypotheses, and at the same time, because of that important pyroclastic target within the Schrödinger Basin, provide access to potentially ISRU relevant resources. Thank you very much.
Questions? The coffee must be wearing off. No questions.
Good. They're all investing in the mission.
Let's hope so. Okay, all right, thanks, Steve.